Okay, so last time I got a little bit of review in. We talked about rules of exponents and worked with radicals a little bit, changing those from radical form to fractional exponents. Then we talked about simplifying radicals a little bit. Got one more topic dealing with radicals we're going to look at, and then the rest of this is still review too. We're going to look at working with algebraic expressions, just refresh ourselves on those. And we'll start working on factoring. We probably won't get done with all that. We're headed. So this rationalizing is the last topic out of section P4. Algebraic expressions out of P5, and then I think factoring is P. Know what goes with what assignment. So first assignment dealing with exponents and radicals is due Thursday night. Some of you have already seen because you've already done it, but I have it set up where if you get the assignment or any part of the assignment, it grades each problem on individually. Each part of the assignment that you get finished more than 24 hours before the due date gets a 5% bonus automatically. So if you were to get the whole thing finished more than 24 hours before the due date, you get 5% on all of it. Even if there's just part of it, you can get done that early. You get 5% bonus on part of it. But they're just trying to encourage you to not get behind. That is my thing. So let's look at some radicals. When we talk about rationalizing radical expressions, the situation we find ourselves in is when we have something like 1 over square root of 2. Sometimes we won't consider that fully simplified. Yes. Yeah. I don't have any way of sending out email reminders and WebSign. I will try to keep you up to date as we come to class on what's coming. That's a good question. I don't have any automated way of doing that. Talk to Cengage. I'm sure they could do. So if we find ourselves in a situation like this, the key thing here being that we have a radical in the denominator. In that case, sometimes we'll be told we need to rationalize expression. So saying there is we want to have a rational number, the denominator. So rational numbers, short version, okay, we don't want a radical. Whatever denominator we end up with to not have a radical. So on this one, just copying the same thing. Try to remember how we can rationalize this. How we can get rid of that square root of 2 in the bottom. So our goal, we don't want to change the number, right? Like if you take this thing and you type it into a calculator, you'll get some decimal, and that'll be like the decimal estimate version of this number. So this is like the exact version of the number. We don't want to change the value. We just want to change how it's written. So our trick here, we're rationalizing, we can multiply by something, but we got to be creative what we multiply by because we don't want to change the value. So can you think of a number you can multiply another number by and it not change the value? So like if I have 5, and I want to multiply it by some number but not change the value, yeah, we can multiply it by 1, right? Because 1 times anything, it stays itself. So all we're going to do when we rationalize is we're going to multiply by a fancy version of 1. Multiply by a fancy version of 1 so that we can rewrite this thing without a radical in the denominator. So our fancy version of 1 we're looking for on this one, turns out we're going to multiply by square root of 2 over square root of 2. Because if we have a number over itself, square root of 2 over square root of 2, what's that going to equal? 1, because it's something divided by itself, it's just going to be 1. That's our fancy version of 1 that we're multiplying by. And when we multiply fractions, okay, maybe it's been a while since you've had to do that. When we multiply fractions, we just multiply straight across. Multiply the tops together and the bottoms together. On this one, on the top, we've got 1 times square root of 2, so that's just square root of 2. On the bottom, there's a couple ways you could think about what we get. Maybe you could think about it this way. We've got square root of 2 times square root of 2. That would be square root of 2 squared. What's nice about that? We have a square root and we square it. What do we get? Square root of 2 squared just gives us, back, I guess. 2. It's okay, even if you guess wrong. It gives us 2 because when we square the square root, it's like they cancel out. 2. Now our issue is solved, and we don't have a radical in the bottom anymore. We got one in the top. That's okay. We don't have one in the bottom anymore, so we would say we have rationalized that expression. Another way you could think about what happens there, so like from bottom, you could kind of switch the order, and it's okay too to think about it that way. You think about this as the square root of squared, or you could even think about it the square root of 4. You get the thing. Slightly different path, a little bit different way you could think. Works both ways. So the part we're missing, how do we pick our fancy version of 1 we multiply by? Got to be intentional about that. So the way I chose square root of 2 over square root of 2 on this one, you can really boil it down. If you have square root of something in the denominator, you're going to multiply by that denominator over it, or at least the radical part of it. Here, square root of 2 means I just multiply by square root of 2 over square root of 2. When we have ones that are slightly trickier, it may be better to think about we want to multiply by something that's going to give us a perfect square in the bottom. So here, perfect square, you can think about it that way, or you can think about square root of 2 times square root of 2. The actual rule is you multiply the numbers underneath the radical together. So we would get square root of 4. Square root of 4 is let's look at another one. The rationalize 3 over square root of 5. So our goal We want to rewrite this thing. We don't want to change the value, but we want to rewrite it somehow where we don't have a radical in the denominator anymore. Square root in the bottom, square root of 5. So I need to multiply by something so I don't end up with the square root anymore. One way I can do that is to multiply by square root of 5. And we're doing that to the bottom, we need to do the top as well. So, because we don't want to change the here, we could multiply by square root of 5 over square root of 5. I'm going to write this one down just a little bit different because it's one more way you can think about it. What happens on the bottom. Top, 3 times square root of 5 is easy because there's really nothing to do there. We just get 3 square root of 5. The only way you can really do the arithmetic with radicals is if you have a radical on both of them. On the bottom, maybe this is kind of the third way to think about what happens. That's the square root of 5 times 5. 5 times 5 is 25. And 25 is a perfect square. Square root of 25. Could have done the other one that same way. We could have said on the bottom we get square root of 2 times square root of 2 square root of 4. Think about it any of those three ways. Whatever works best for your brain. So the idea, if you take this, 3 divided by square root of 5, put it in a calculator. Take this, 3 times square root of 5 divided by 5, you'll get the same decimal. We haven't changed the value, we've just changed how we write it. Okay. Question so far? Okay, let's do another one. This one's a little bit different, kind of adding in a little bit of information. What if we want to rationalize that square root, and then inside the square root we've got the fraction 3 over 2. Adding in a piece of information here, a little bit of review. We want to take the square root of a fraction. That is the same thing as taking the square root of the top or the square root of the bottom. So these two, same. Now what? If we want to get rid of the square root of 2 in the bottom, this one, what should we multiply by? Square root of 2 over square root of 2. On the top this time, when we multiply, we can actually multiply these out. Square root of 3 times square root of 2. We multiply the numbers underneath the radical, so 3 times 2. Square root of 6 on top. Bottom, square root of 2 times square root of 2, that's square root of 4. Square root of 2 squared, however you want. So the bottom's a perfect square. Square root of 4 is and one thing you may think about, could we simplify square root of 6, break it down to prime factors 2 and 3, so we don't have 2 of anything under there, so simple as we can make it. On that one, that's really just adding in fraction I did. Yeah, one more. We won't have many of these, but one more. It's a little bit, maybe a little bit trickier. So, so thing that's different on this one, we don't have a square root in the bottom. Got a cube root or a third root. Trying to get rid of that radical, trying to get rid of that cube root. Need to end up with a perfect cube, not a perfect square. This one's maybe a little bit trickier thinking your way through figuring out what we should multiply by. One way we can think about it is we've got a cube root of 2. So we've got one of them. We end up with 3 of them. That'll turn it into a perfect cube. Because we'll have cube root of 2 times cube root of 2 times cube root of 2. Cube root of 2 to the third. 2 cube root of 2 cubed. A perfect cube. So, what should we? Short way of writing it, we need 2 more of these things. So, by root of 2 squared over it. And the idea there, maybe it'll make more sense now that it's written down. The idea there is we want to end up with 3 of these things because it's a cube root. If we end up with 3 of them, cube root and the third power will cancel. That makes the top just a little bit messier on the other ones we did. 5 just comes along. 5 times something. Top, if we want to simplify that, that's cube root of 2 squared. So the way you could work that out is cube root of 2 squared underneath there. 2 squared is squaring the 2. On the bottom, we won't leave it like this, but what we're getting, our goal, we've got cube root of 2, got 3 of those now, cubed. And the whole reason we did that was so the cube root and the cube cancel. So the cancel on the bottom, we just that idea you can extend to any index on the radical. So this had been a 5th root instead of 3rd, 3. Then we need a total of 5 of these things. We would, if this was a 5 instead. So we've got 1 here. So what we could do is, again, if this was the 5th root, over here, change this to a 4. So we'd end up with 5 of these things. Whatever this number is, you just want to end up with a total of that. We won't have a lot of those. panic if it doesn't seem as easy as the other one. Questions on that one? Don't be shy. Try not to be shy. Huh? Yep. So so we got one cube root of 2 here, 2 cube roots of 2 there, so we end up with 3 of them. And then the cube root and the cube cancel each other, so we end up with the 2 that was under here. Yeah, so that cancels out. Yeah. So if this was another number, if this was 7, then you would have 7 here. These would still cancel, and you end up with, yeah, the 2 underneath the cube root doesn't really matter what it is. That one just. Other question? Okay. Everything we needed to finish that one up. Yeah. Next little review section is not bad. The P5 assignment. Section we call algebraic expressions. We're dealing with expressions, mathematical phrases, if you want to think about it that way, that have variables involved. But we call them expressions, not equations, because we don't have an equal sign in here anywhere. A lot of this stuff you may be familiar with from solving equations. Just in this section, we don't have an equal sign to do. So algebraic expressions, I'm talking about things like that would be an algebraic expression. Have a variable involved. Algebraic. For that would be an algebraic. A little bit of vocabulary that goes along with these, just to make sure we're on the same page. This first one, first one I would say has 2 terms. It's an algebraic expression with 2 terms. I would say this is term number 1, right, the x cubed, and this is term number 2. So anytime we have parts of an expression separated with a plus or a minus sign, splits it up into different terms. And the second one down here, how many terms would we say that one has? 3. Yeah. So we would say the x squared is 1 term, 2x is 1 term, and then 5 is 3 terms. Wanted to cover that real quick just so we can say, combine like terms or add these 2 terms together. Idea of what we're talking about. So our goal in reviewing in this section, we just want to talk about how if we have algebraic expressions like these, how do we add 2 of these things together? How do we subtract 2 of these things? How do we multiply these things? Stuff you've seen before. May or may not have been a while. Talk about how to add. So got a plus sign between two of these algebraic expressions I want to add. Adding these things is not overly complicated. Really, all adding is just another way of saying we want to combine like terms. What do we mean by like terms? So figuring that part out, we look at the variable involved with each term. If the variable in one term has the same exponent as the variable in another term, we say they are like terms. Or if we have more than one variable involved, we have to check each variable in each. Here we've only got the x. So here, first term in my first expression, I've got a 2x. So over in the other expression, I've got a like term because I've got a x. So that's the exponent on both of those. They're like terms. So to combine these, it's plus. Combine these, I know I'm going way back. Combine these, I've got 2x plus 3x. And it gives me 5x's. And I've got two more like terms. I've got the plus 1 and the minus 4. So they're like terms because they don't have a variable. The way we could talk about those is we could call them constant terms. So I want to combine those two. I've got a plus 1 plus -4. So 1 plus -4, or you can think about it as 1 minus 4. There we would end up with adding two algebraic expressions. You just look for like terms. Have like terms, you add them or subtract them, however the signs work out. Have some term that doesn't have a partner, then it just comes along for the ride. Okay. Not a lot to talk about on adding. So, question on these then? What about if we want to subtract? Subtracting is only just a tiny bit trickier. A couple more algebraic expressions. Minus 3x plus 7 minus plus 1. We're really still just after combining like terms here. There's only one other thing that we have to be a little careful about. And that is that this is telling us to subtract the whole second expression. So we've got to subtract the 2x squared and we got to subtract the 1. So the way we typically think about that is that we have a minus sign out front of that second one, so we want to change colors here. We want to apply that minus sign or distribute that minus sign to everything in that second expression. So we can, after we do that, we can drop the parentheses. On the first one, you really don't have to have the parentheses there. They don't do anything. You're subtracting, they do something. They tell us to remember to distribute that minus sign. After we do that, we don't need them. Nothing's happening with the first expression here. But then we had positive 2x squared. We got to change that to minus 2x squared. And also, got to apply that negative to the plus 1, so it turns into minus 1. Okay, remember to change all the signs in that second one. Now we just combine like terms. What like terms do we have to combine here? The like terms? Yeah, we got a x squared term and a negative 2x squared term. Those are like terms, so x squared minus 2x squared will give us negative x squared. What else do you? Yeah, 7 and negative 1 are like terms. They're both constant terms. So there we got 7 minus 1 will give us positive 6, and I'm going to leave some space because we've got one that doesn't have another like term in there. We got negative 3x. We don't have anything to combine it with, so it just stays negative 3x. You don't necessarily have to have everything in this order. This one, that's just kind of our standard order. Write them in. Still knows. Just something you got to remember. If you got trying to subtract expression like that, you got to change all the signs after the. Not hard to do, but it's easy. Okay, so there's adding and subtracting, and now we can look at slightly more interesting. Multiply algebraic expression. If you're bored to death, hang in there. Okay, this seems easy to you. Hang in there and just be glad that multiplying. So look at our first way we can multiply these. Here we're multiplying two algebraic expressions. Multiplying 3x times 4x minus 6. So the thing we have to remember is that 3x, we got to multiply it by the whole expression comes after it. If I remember what little technique's called, what property we're using? Distributive property, yeah, distributive property. So the idea is we want to multiply the 3x not just by the 4x, but we want to multiply it also by negative. Got to do both. So do 3x times 4x. 3 times 4 is 12. X times x, what's that give us? X squared, yep, x squared. And 3x times negative 6. 3 times negative 6, negative 18, and we have an call this distributive property. Got to distribute 3x. That's true. So on this one, our second algebraic expression, I gave us two terms, 4x minus 6. That's true no matter how many we have. Okay? If our second expression had 5 terms in it, you would do the 3x times all 5 of them. Property. All right, we got another technique that comes into play a lot. Really, it's just the distributive property again. do it when we're in a situation that looks a little different. Time our first expression has two terms and our second expression has two. So we give this situation its own little nickname. You may remember what we used to multiply something like this out. What kind of it's the reverse of factoring. What you may remember what method? Yeah, somebody got anybody? Yes. We normally call this full method. And so that's multiply the first terms together, multiply the outer terms together, multiply the inner terms together, multiply the last term. FOIL. What we usually use to remember. Really, all it is distributive property. So what we're saying is we need to take 2x, distribute it to both terms in the second one. That's the first and the outer terms. And then we take the -1 and need to distribute it to both of the terms. That's the inner and the last term. Really just distributive property. But that's the order we normally do it in. Technically, if you do a different order, as long as you get all the multiplications done, end up with the right answer. It may just be in a different order. But here, we do the first terms, 2x times x, x squared. Do the outer terms, 2x times 7, 14x, positives, plus. Inner terms, -1 times x, x. Do the last terms, -1 times 7, that's 7. And we want to simplify as much as possible, so let's see if there are any like terms we can combine here. Our middle terms are both x terms, so combine those. We've got 14x minus x. On that one? Yeah. Some of it coming back to you? Maybe some of you are a little rusty on. I kind of refresh your memory. Forget exactly how the rules work on. Okay. Let's do one that's a little messy then. Wrap this little section up. Let's do what we've learned to work. So this one, we've got two variables. We've got x and y. First expression has two terms. Second expression has three terms. So really just extending the idea of FOIL method. What we want to do is we want to take the x cubed term and multiply it by all three terms in second expression. After that, we'll take the -y term and multiply it by all three. And we'll see what kind of like terms we have Combine those to clean things. All right, so let's start with multiplying the x cubed by everything. So x cubed times 2x squared, 2x to the fifth. We add the exponent. We got x cubed times negative xy. That'll be negative x to the fourth y. Got an understood exponent of 1 on that x. And the last one's a little easier. We got x cubed times 3, so now we've got to be a little careful on this next one because we have a negative y, so we've got to really keep track of the signs. So negative y times 2x squared, so it's going to make it negative. Got a 2, x squared. If you put negative 2yx squared, that's not wrong. Typically, we have multiple variables. We write them down in alphabetical order, but nothing really wrong with it. If you All right, then we do negative y times negative xy, so both negative, so it's going to turn positive. Got the x, nothing happens to it, but then we've got y times y, so it's y there. Again, the last one's a little easier. Negative y times 3 is negative. And let's see. See any like terms? I don't. Here, this one's x to the fifth. We don't have any other x to the fifths. This one, we've got an x to the fourth. Nothing else has x to the fourth, so that's all we use. This one got x to the third. Nothing else got one of those. Got x squared. Nothing else has got one of those. This one's got just an x, or you could look at it. It's got a y squared. Nothing else has that. Last one just has a y. So I actually didn't have any like terms on this. Big mess for our answer. Questions on that one? Any of the exponents or signs or anything you're unsure where they came from? For sure, if we work a problem together, you don't want it to look like magic. Okay? If stuff starts looking like magic in math class, that's bad. You need to back up until see what was going on and then walk back through it. Okay, no shame in that whatsoever. So start feeling like you're in magic class instead of math class. Let me know. Next review topic. Last one we had on our list. We probably won't get finished with it today. At least get going on it. And it's factoring. And to be more specific, we want to factor polynomials. Short version of a polynomial. Okay, we'll get a more formal definition later in the semester. Short version of a polynomial is it's just algebraic expression. Got the different powers of x we can have, the different coefficients with formal to say that. So we could say factoring algebraic expression. So got a little bit head start on the first little idea in this section. First thing we kind of need to talk about is how many terms each polynomial has. That's the same idea as with how many terms an algebraic expression has. So we got something like this. That one, say, just has one term, because we don't have any plus signs or minus signs in there, and to split it into separate terms. One term. That one has two terms because we've got that minus sign that splits it into two pieces. Let's one more here. That one we would say has three terms. We're about to give these special names. So we could say this is an algebraic expression with one term, or another way we could talk about it is we could say it's a polynomial with one term, and we give that a special name we call a monomial. Because it's a polynomial with one term, monomial. The generic name for these is polynomial. Poly just means many. Two terms, came back, I guess. Binomial. By many. Here. Three terms. Trinomial. These are the common ones that come up as far as the names. Specifically, we're going to talk about, maybe Thursday, we're going to talk about, might get to it a little bit today, talk about specific techniques for factoring trinomial terms. Want to know, it means it has three terms. So, look at our different factoring. Technique number one, we're going to look to see if we have a common factor. Call it the greatest common factor, because if we do have a common factor, we may have more than one. We want to take out the greatest common factor. So factors of a number, little side note here, like if we got 6, we want to talk about factors of 6. We're talking about numbers we can multiply together and get 6. So one example of factors of 6 would be 2 and 3. 2 times 3 would give us 2 is a factor, 3 is a factor. Got one other way we could come up with factors of 6. What are the other two factors? 2 and 3 or 1 and 6. So you always got the possibility for factors of being 1 in itself. Same thing's true with polynomials. We're really going to ignore that situation. It doesn't really do us any good to factor out a 1 most of the time. So I'm looking for non-1 factor. So when we factor polynomials, we mean the same thing. We want to know what could we multiply together. We're thinking about polynomials. What polynomials could we multiply together to get the polynomial we start with? So look at one. Here's 6x squared plus 3x. Want to factor out a common factor, factor out the greatest common factor. We're looking at each of the terms. Here we've got a binomial, so two terms. We're looking at both of the terms, looking to see if they have a factor in common. Factor. If they do, we want the biggest factor there. Yeah, 3. So 3 works. So if we're looking at the number parts, we've got 6 and 3. They do have a common factor of 3. We'll write that down. So on this one, we've got something else in common because we also need to consider the variable parts. Yeah, so they both have an x in common. And the thing to look for there, since they both have some x's, which one has the least, and whichever one has the least, we've got that many in common. Now, this one has 2 x's, this one only has 1 x, so we could say we have 1 x in common, or x to the first in common. Have an x. And then the idea is we want to know if we divided 3x out of that, we factored 3x out, what would we have left? Maybe an easier question to answer, easier way of thinking about it, is what would we have to multiply 3x by to get back to 6x squared? So to get from 3 to 6, we would need to multiply by 2. To get from x to x squared, we would another x. X times x. Then we need to check the same thing for that last one, but that one's pretty easy. What would we have to multiply 3x by to get 3x? 1. There, we've taken this polynomial, squared plus 3x, and we factored it out. We've got two factors here. First factor is 3x. Other factor is 2x plus 1. And the good thing about these is you can check, make sure you did it correctly. Because all we would have to do to check it, we multiply it back out. So we'd use distributive property here. 3x times 2x is 6x squared. 3x times 1 is 3x. Yeah, that works backward. This is factored. Factored. Look at another one real quick. Now, now we have 3 terms. So when we're looking for a common factor, it has to be common to all 3 terms. If you look at the number part, the coefficient part, we've got 3, 6, and 6. See any factors that are common with 3, 6, and 6? 3, you can divide all of them by 3. Got a 3 again. Variables that all have x's again. But how many do we have in common? 4. We got 4, right? Because that's we don't have 6 of them we can take out because this one doesn't have enough. We don't have 5 of them because this one doesn't have enough. So look at the smallest exponent. It has 4 x's. That's the most we can. X to the 4th. X to the 4th times what will give us good on the 3 part, but we need x squared. Yeah, or you can write a 1 if you want to. You don't have to write the 1. Okay. And we've got 3x to the 4th. We're trying to get to 6x to the 5th. So get to the 6th, we've got to multiply by 2. And get from x to the 4th to x to the 5th. We need another x. On the last one, we're trying to get from 3 to 6, so we need a 2 again. And we've got x to the 4th. We're trying to get to x to the 4th, so do we need any more x's? Nope. So we've taken out the common factor there. Questions on doing that? All right. Do one more. Yep. One's a little bit messy. Here, but it's okay. We just look at one piece at a time. Just look at the little piece, break it down into parts. Got a -4, 24, and a 28. Any number that'll go into all those? 4 works. 4 works. Should take out a -4. When it comes to the numerical part, it's really always an option. Because if you factor out a negative number, all it does is it changes the sign. Factor it out. Here, we don't have a good reason to take out the negative instead of the positive. Okay. So got the number part, coefficient part. So now we can look at the x's in each one. We got x to the 4th, x, x. So what can we take out? X. Yeah. The most, or the, yes, the most we have in all of them. We look at the y's, we've got y squared, y to the 3rd, y to the 4th. Y squared, yeah, y squared's the most we can take out. All right, so trying to get from 4, -4, so we've got to have a negative. You can write -1 if you want to. We're trying to get from x to x to the 4th, so what do we need? X to the 3rd, that's it. And we're trying to get from y squared to y squared, so 1, we don't have to write a 1 down. Second term, 4 to 26, 24. 4 to 24, we need 6. And got an x, we want to end up with 1x, so we don't have to do anything there. And to get from y squared to y cubed, we need y. Last one, to get from 4 to 28, anybody remember? It's a little bit hard to remember sometimes. 7, I think I heard several. 7. Got an x, we only need 1, so we don't have to put anything else. And got y squared, we need y to the 4th, so y squared. Even if they get messier, it might take a little bit longer, but they're not harder. One more little bit. Okay, one more little bit. I'll still let you out a little early. Okay, let you out. We're 45 to 2:15. I'll make sure I let you out. Well, let's just do the simplest version of trinomials. Stop there. We'll have just a little bit of this section left to do. So trinomials, and we want to factor those. I tend to break it down into two cases. So here's let's get a trinomial. This is what I would say is the easier case, factor into trinomial. And what I'm looking at when I say this is easier case is I'm looking at the coefficient, the number in front of the x squared, 1. That number is a 1, x squared, then life's a little bit easier trying to factor these. We'll talk about what to do. So that we call it the leading coefficient, the coefficient on the variable with the biggest exponent. We call it the leading coefficient. Our leading coefficient is a 1. And what I'm going to do is I'm going to 2 sets of parentheses ready down here. And what we're doing, we're thinking reverse of the FOIL method. So to get this leading term, first term, x squared, what has to multiply together to give us x squared? We got to have, we got to have x times x times. So those are going to go in the first spots. Then figure out the rest. We've got to, it's a little bit trickier because we've got this middle term we're dealing with. We got to know how that middle term came to be, because remember when we do FOIL, a lot of times we have like terms to combine. They've like already been combined on this one. So the way we kind of decode that, figure out what needs to go where, is we look at the constant term, the last term. We want factors of this, numbers that multiply together to give us the factors of 4. We want factors of 4 add together, or sum, if you want to put it that way. Middle number. Add factors of that last number, multiply together to give us 4, but when we add them up, 5. So we don't have a lot of factors of 4 that we have to check. We can go off and do scratch work on the side if we need. So factors of 4, what can we do? We can do 1 and 4, or we can do 2 and 2. Yeah. So 1 plus 4 does give us 5. That's what we're looking for. The other two don't work, right? Because if we do 2 plus 2, we get 4. Trying to get 1 and 4, the ones we're looking for. So we can just fill those in. So they're both positive, right? So plus 1. And we can check ourselves. Make sure that our factors are correct. A lot of times you'd catch your mistake. Check it. We're doing FOIL method to check it. So x times x is x squared. Times 4 is 4x. Times x is x. 1 times 4 is 4. And when we combine like terms, x squared plus 5x, like we want. Except this is correct. Let's do one more and I'll let you go. Maybe we'll do one or two more of these to get us warmed up next. So our leading coefficient there, the coefficient with the x squared is a 1 again. So how am I to? This time we got to think about the sign because it's not a positive number on the end anymore. It's a negative number. So over on our scratch work, we need factors of negative 21. So the ways you get a negative number, or the way you get a negative number, is one of the factors is negative and one of the factors is positive. So when we're listing out our factors, we gotta, don't have too many here. We got 1 and 21, or 3 and 7. Remember what we're trying to get. We're trying to get positive 4 when we add them up, but also remember one of our factors has got to be negative. So we look at 1 and 21. That's not going to work because we do that. We get negative. We get 20. That we get negative 20. We do that. We got negative 3 and positive 7. Gives us 4. So we're in good shape there. Again, we got to have x times x to get x squared. Then we want minus 3, positive 7 to give us our positive 4 in the middle. And we check it. Should check it, at least in your head. X squared plus 7x minus 3x minus 21, so x squared plus 4x minus 21, x out. All right. They're crazy. I'll let you go today. We'll pick up here Thursday. We'll do a couple more of these maybe to get warmed up. And I'll see you then.